Hello. So, we've seen sort of generally what concavity is and, again, generally what it looks like, but now we want to figure out, okay, how do we determine the concavity of a function? So, sort of classically in most of pre-calc classes, you probably discussed sort of how to determine concavity from a graph, but this is sort of far enough along now that we sort of run into functions where the graph is just too complicated to sort of immediately see, right? And if you're looking at a really complicated function, you can't just be like, oh, picture the graph in your head and figure out the concavity. Like, most people can't do that. So we want another way of doing this sort of more rigorously with, algebra and, shockingly, calculus. So that's our goal. So remember, concavity sort of visually, as a starting point, can best be thought of as this sort of force pulling the graph, trying to bend it either in a positive direction, meaning this is what we call sort of concave up, or in the negative direction, which we call concave down. So this doesn't sort of necessarily, and sort of importantly, in fact, doesn't correlate with the function being increasing or decreasing. This is one of those divisions that your brain as a visual entity wants to put these two things together. So this is usually one of the sticking points for a lot of students, is trying to separate these ideas. So it's sort of really important to think carefully as we move forward with concavity and sort of separate in your head the idea of increasing or decreasing from being concave up or concave down. Because it's not that these things always go together or never go together, it's that they are in some sense completely separate things, okay? So let's look at an example. So here we have a piece of a curve, and we can look at this function and see, right, traveling from left to right, that we are increasing as we go across this curve. So this function is increasing up to the point B, right? So if we go from A, we're going up, 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 all the way to B, and then from B we are decreasing. But this entire time, it is also concave down. So what this concavity is doing is it's in some sense affecting how fast the function is increasing, okay? So the sort of key here, though, is that the concavity is the rate of change of the rate of change, right? So this is sort of the same idea as being the derivative of the derivative, also known as the second derivative. So concavity is sort of inherently linked to the second derivative. This is what we're going to sort of develop in this video. As a maybe more, again, visual interpretation, if this is helpful, this thing being concave down while increasing, you can think of it as it's, again, it's trying to increase as it goes up, but that concavity is sort of this constant drag, making it increase less and less quickly until eventually at B, that concavity overpowers it, and now it's starting to pull it back down, okay? So again, it's this sort of change of the rate of change. Now, before we dive into that, we have to take a second here, as we're sort of introducing this idea of a derivative, that there's sort of notation for these, what are called higher derivatives, meaning if we keep taking a derivative, how do we notate that? So when we take multiple derivatives, there's really sort of three common ways to represent this with notation. I will say there are three common ways. There are lots of ways of representing this, sort of that are discipline specific. So we're going to do the three common ones you'll see in most any undergrad class, in most any setting, right? Most physics classes, engineering, mathematics, they'll all use one of these notations. But that is not to say that you won't run into a different notation in some very specific class. So just, again, keep this in mind. These are the common ones. So first one, we can add an additional tick mark, right? So we're used to the f prime, as it's called, or f with one tick being a first derivative. So here, now we have two tick marks. This would be the second derivative. This is really by far the most common way to write a second derivative because it's just another tick mark. It's pretty easy to do. You can do this with a third derivative too, right? So you can also have this with 3 tick marks, but at this point it starts to get a little unwieldy, right? If you have 27th derivative, you don't want to have 27 of these little tick marks. So really, the first and second derivative, very common to see this notation. The third derivative, it's about as common as the next one we're going to look at, which is this kth derivative. So here we have f, and then it looks sort of like an exponent, but importantly here, it has parentheses around it. Those parentheses, right, as we can see here, if we wanted a third derivative, those parentheses are actually really key because that is telling you it's a derivative and not, say, the third power or something like this, okay? So the parentheses are actually very important in this notation. You need to keep those. You can use this for any level, so strictly speaking, you could put a 2 there or a 7 there for the second or seventh derivative, and that would be notationally correct, but usually don't see it until 3 or higher, okay? Lastly, but not sort of least, we have if you remember that like df dx or dy dx form, you can do this for higher derivatives as well. Again, where the k goes is actually really important here. So you notice that the k is on the d in the top, but on the k in the bottom. So this tells you it's the kth derivative on the top, and the bottom is telling you it's with respect to x each of those times. Again, this is one of those things that is sort of very common in very specific settings, more commonly in multivariable settings where maybe it's not with respect to x every time, but that's not something we're going to run into in this class. So in this class, it's probably more likely that you'll see one of the other notations, but we'll try to fold in that, df dx version every once in a while, just so you're sort of familiar with it. Again, you can put whatever number. So, we have an example of the third derivative because second derivative is usually done with tick marks. So you don't usually see this until you hit 3 or higher, but you could put into 2 or a 17 or whatever level you need. Okay. That just tells you how many times you're taking the derivative the whole way through. All right. So back to what we were talking about, concavity. So our theorem, again, we'll sort of do the official statement and then translate it into more human speak. So the theorem says, okay, if you have this function f, it's on sort of some interval and it is a real valued function, and it's second differentiable, meaning that we can take a second derivative. Then if we have some value between a and b, some x value we can use, if the second derivative is positive, then f is concave up at that point. If it is negative, then it's concave down at that point. So sort of in more human speak, what this is saying is as long as the second derivative makes sense, right? You can take the second derivative and you can plug in a point and you don't have, crazy domain restrictions or something stopping you, then you can use the sign of whatever you get, right? If you plug in 15 and you get a 7 out, that's positive. That tells you that this thing is concave up at that value, okay? So that's the sort of human version of this theorem. So again, let's look at some examples here. So let's say we have this function, f of x is x cubed minus 2x squared plus 1. So the first step, if we want to talk about concavity, take the second derivative. So I take one derivative, which would get me 3x squared minus 4x. Take a second derivative, that gets me this 6x minus 4. Let's say I want to know the concavity at some specific value like 5. Well, I just plug in 5. That's all I need to do. And what the output is, in this case 26, that will tell me, right? Since 26 is strictly positive, that tells me that we're concave up at 5. Okay? That's really all there is to it. It's not any deeper than that. Why this is useful and when we use it, then we get into deeper stuff. But that's all that the second derivative really is sort of using or doing here is telling us exactly the sign, right? Notice I'm not caring that it is 26 as opposed to 27. I care that it is positive versus negative, okay? So what do we do? Concavity is really sort of a way of measuring the rate of change of the rate of change, right? So in this sort of rate of change parlance, right, in this sort of language that we use in calculus, that really is telling us that concavity is measured by this second derivative. And sort of as a side piece of that, then, we discussed these common notations of how to do higher derivatives. Because as we move forward, now that we're taking second derivatives, we will inevitably be asking questions about third derivatives or fourth derivatives, right? So it's sort of useful to know how to write this stuff down. So we covered sort of the basic common versions of that you'll see. Okay. So that is that.